Well, seems like we got a good number of people here, so maybe let's go ahead and jump into it. Um, Thanks everybody for showing up for this, to making a splash with the Stratasys NEO stereolithography machines. These are, a newer technology to the Stratasys umbrella. It's going to be new to a lot of people's introduction to 3D printing, at least in this format, very different from the FDM and PolyJet methods. So we're going to dive into a little bit of how it works and different materials and how you can leverage it, just as an initial kind of overview on this technology that's been around for a while but new to a lot of people. If we jump in, let's introduce ourselves real quick, assuming I can. There we go. Our presenters today are twofold. We have Tim Crennen, that's me, the one on the right side of the picture or on the webcam right now. And I've been in the additive industry for over 10 years, working on 3D printers from all variety of technologies and all different applications. And then joining us today also is Simon Pinter.
Simon Pinter. I'm also one of the application engineers here at GoEngineer. However many years of experience Tim has, I have that many minus 1 day.
Plus two.
Plus two. Yeah, I have worked with Stratasys machines since about 2012. So we're really getting up there in age, but been using stereolithography since about 2013. So we go way back. We go way back with the polymers.
Right, and it's an interesting technology. It's been around for a long time. But we'll go ahead and jump in. I'll probably turn my webcam off real quick so it doesn't distract people too much. But moving along, we're going to start into our prologue for the NEO stereolithography. And in general, it's an interesting technology. So it brings a lot of unique advantages to the additive manufacturing rapid prototyping world. So it has great accuracy, great injection molding quality, great, really high surface finish parts, and they're very reliable nowadays. And with that, you can get low cost per part because you bulk buying the resin that you use in these. And applications can be used in all sorts of things, from general concept prototyping, investment casting, surrogate parts, functional prototypes, things like that. But with that, I mean, the stereolithography technology has actually been around for a long time. It's actually one of the earlier additive manufacturing technologies ever invented. And so how old is it, Simon? It's been around since the 80s or earlier, right?
Yeah, it's been around since the mid to late 80s. Older than me. Not by a lot, but by a little.
By a little. And with that being one of the first technologies that came out a long time ago, it had a lot of issues that have kind of been put on the wayside as people have been looking at other different technologies that have been coming out. And some of the issues that they ran into back then were, aging systems because they came out a long time ago. But they were locked systems. They didn't have the versatility. The software never had proper updates to it and stuff, so it'd be buggy. They couldn't get as high of accuracy and resolution because these things were developed and worked on a long time ago. And part of the locked systems, you have to only use what the manufacturer allows you to, whatever specific materials they have. And the ones that worked out there for a while were pretty good and people were using them a lot, but then they're starting to age as they came out in the 80s, 90s, and people have just been using those systems for a long time. And so the reliability just keeps going down and down as they keep getting older and older.
Well, and it's also important to differentiate that they stopped innovating. The folks who first started producing stereolithography machines in the late 80s, the technology didn't change so much for the next 30 years. Material science has gotten a lot more advanced, but fundamentally the construction and workflow for stereolithography really didn't have a whole lot of innovation. So Tim's next slide is going to start to tell the story about how the NEO kind of takes it to the next level.
That's right. And yeah, with the new innovations that they've kind of reinvigorated the stereolithography with in these NEO systems, it kind of runs the gambit where they upgraded pretty much all the different aspects from the build size, and the build chambers on these are much more larger and dramatic when you get up to the NEO 800, which 800 by 800 millimeter build area, and catty corner you can get pretty big. But then also open vat systems to allow customer choice. So it's an open material system, as long as it runs at the proper wavelength, which we'll get into how these machines actually work in a little bit. As long as it's the right compatible material for the system, you can run any material you want on it. And because that's a big advantage, these technologies have been around for so long, there's actually a large selection of materials out there to pick from the Somos validated materials to a whole bunch of just open world materials that past 30, 40 years of research have done on it. And as Simon was hinting at, the material science being increasing and getting better, stronger, more durable, higher performance materials out there is really what's making a lot more use out of these machines. And then on top of that, they've done lots of innovations to make part quality and reliability much higher. Reusability and the functionality of the machines is very high with the new softwares, the ease of use on them for being able to generate the supports, and the slicing is all kind of done behind the scenes in the Magic software, which is all industry standard prep software. Makes using these machines very easy. So we kind of have two different technology or two different sizes of machines. We have the Neo 450 and then we have the Neo 800. And if you ever forget which size build volume the machines have, it's kind of in their name. So the Neo 450 is 450 by 450 millimeters and 400 deep. And other than that, they're all the same for the same, laser resolution of 355 nanometers for the types of resin you can run. And you can do high quality parts, high reliability machines. The 450 can actually do a bit higher quality parts than the 800, because the 800 is more specialized in printing much larger parts. But you can see on here, the 800 is 800 by 800 millimeters, shocker, and 600 millimeters deep. So you can do very large parts, and you can kind of see in the pictures of parts we'll be showing, big clear parts, durable parts, super smooth, high surface finish things. But we'll go ahead and jump into how the actual stereolithography technology works. We'll give it a quick overview here. So starts out with the laser. So it actually has a laser generator up there that uses to make the specific 355 nanometer wavelength laser beam to shoot out to actually cure the resin. And all these resins we're going to be working with, it's a photoreactive photopolymer that fills the entire vat, and then we're going to use the laser beam to draw our cross section on there to cure it wherever the laser beam hits, and then keep building up. And so each step of that process we'll go through real quick. Once you have your laser beam, you got to do something with it. So first thing we need to do is focus it properly. So that comes down to our Z galvanometer, or the Z galvo as we call it. And this actively focuses the laser beam during the build to get a specific spot size. And one of the cool things about that is because it's active, it's changing all the time as it's drawing, partly because as the beam goes out to the sides of the vat, you're going to start getting different focal lengths and stuff you need to adjust for. But also we can change the beam diameter as we're building our part. So when it's trying to draw the outline of your part and then fill it in for the cross section, it can do a tighter beam on the profile and then go to a bigger, fatter beam when it's doing the infill to fill it in faster.
So I was just going to add one more point about the functionality of this laser. I think the folks on the call are already kind of putting two and two together, but the way stereolithography works, and we're going to dive into this a little bit more deeply, but the way stereolithography works is you've got a single laser point that's basically tracing tool paths, so that UV light hitting the resin, it is needing to both trace the outline of a slice, as well as Tim was mentioning, filling in the interior with a cross-hatching pattern. And Tim, I think you touched on how the Z-Galvo can make the beam wider while it's doing the cross-hatching and narrower for the fine features on those outer contours.
Right, and how it's actually moving that beam around is with the XY scanners. The next step that it hits, so the beam goes through, it gets focused to wherever it's going to need specifically on the platform. And the XY scanner actually bounces it down, points it at the resin, and controls where it is and can drive it around. So there's a nice mirror assembly in there, but it can drive the beam around up to 10,000 millimeters per second around the surface of our vat. So it's not always going to be running at full speed. It's going to, all these things are done in the back end of the software to go at whatever speed it needs to get proper penetration, proper cure. It depends on the beam diameter, the laser power, how fast you want to drive it around. all that is compensated for, and all that is done in the back end in the software. So we never really have to go in and tweak those settings unless you're trying to dial in a new resin or something. Once you get it set, everything's good to go.
Yeah, Tim, do I have to be an expert in programming XY mirrors or Z galvos in order to get this to trace out my geometry accurately?
You do not. You don't have to know anything about doing CNC programming or any of that. It's about as easy it is to run any of the other additive machines out there from FDM or PolarJet, where you just bring in your CAD file or your STL, and the software will slice it up. The software will generate the support structure, and then you just send that to the printer and tell it to print.
Very cool.
So then the next step here, after we hit the XY scanner and point the laser beam down, now it actually hits the vat. And in the vat, we have a build platform. And it's just, it builds our parts. It starts with elevated support structures. That way our parts aren't fused to the build platform. It's easier to scrape them off. And it draws the our cross section. And then as it builds, it's going to build it onto the platform. Once it's done with that layer, the Z stage will dip it down into the vat of resin. And as this gets, yes.
Sorry, going to interrupt that one just to add one more point about how far down it dips. Important to note that the default layer thickness on stereolithography is 100 microns, but the machine can actually go down to 50 if you ask it nice enough.
You can also go fatter on it too, right?
You can. In the documentation, I've seen up to 200 microns, but I wouldn't be surprised if it let you put something even higher than that. It's just a matter of the settings as far as your laser output and the speed at which it's moving.
Yeah. And as part of the dip where the Z stage goes down, you can go down 100 microns depending on the resin you're running. It might actually dip down farther and then come back up. So it does like an initial coating of material over the top. And then it comes back, goes back up and then right under the surface, holding that 100 micron layers. And then it holds it there nice and flat where we have our recoater blade that goes across and breaks any surface tension that might be there, stops any bubbles, any weld up walls of material. And the recoater blade is actually, it's a pretty advanced piece of technology on this. It's not just a windshield wiper blade or something going across breaking surface tension, which I initially thought when I was learning about it. It actually holds vacuum suction in there and some resin up in this hollow reservoir up there above the resin. And that sucks up any bubbles to break that. It helps break surface tension. It also has that extra resin up there to deposit back on the surface. If you're printing a part that has a big cross section, it cured all that material there. It now needs to get new layer of material over the top. So that gets deposited from that little reservoir that sits inside the recoater blade.
I will also add in my time using stereolithography printers before the Neo, so from other manufacturers, the single greatest point of failure in a build was the recoater blade colliding with the part. I will say I've had my machine, I have a Neo 800 here in my office for about a year, and I'm knocking on laminated fake plastic wood in front of me. I've never had a single build failure related to anything mechanical with the machine. It's only been from me setting up a file incorrectly in software, which is to say this recoater is locked in terms of its rigidity and its precision and its ability to do what it needs to without impacting the part.
Yeah, because they're very stable machines with these Neos. Their entire frame is just a giant cast piece of metal that holds the whole thing rigid, so you don't have any sway, drift in it. When you calibrate everything in with the lasers, you don't want anything to get out of alignment. So they're extremely heavy, rigid machines, so that way everything just continues to work well on them.
Well, and this is my favorite Final Jeopardy question about the Neo, both the 450 and the 800. The single most expensive piece of hardware on the inside of both of the machines, as Tim was saying, the cast iron rails that the recoater moves on. That is the most expensive component of the printer, and that's what keeps that recoater absolutely rock solid and exactly at the height that it needs to be.
And then as it's going across and coating those layers in our resin vat, we have the resin vat. And there's some cool little advantages in there. It does have an internal reservoir to precisely control how much resin is, the level it's at. It doesn't really go up and down because material curing is like expanding or shrinking or anything. It's more because as the Z stage goes down in, we're adding that metal into the vat, it's displacing material. We want to keep that vat at an extremely precise level, so that way the laser beam is hitting the surface where it thinks it's hitting, and everything stays accurate and calibrated. But that's pretty much the rough overview of how the technology in general works.
Tim, I've got a quick question for you, and we may have this covered in another slide, but we're looking at a vat of resin in a really big machine. How hard is it for me to change material?
Well, you would have to change the entire vat out. Wiping down the Z stage and stuff wouldn't be very hard, but what you do, you'd have to have a whole second vat of material sitting there, and then you just get a pallet jack, pick it up, haul it out, wheel the new one in, and recheck that things are level, and you're good to go.
So
but
it sounds,
that is the only downside with that is you need a whole another vat.
So it sounds like this is a technology that's really well suited to organizations that are going to be committing to a particular type of material for their applications for at least a while.
Yeah, that's a good point. This isn't the technology where like FDM or PolarJet, we're like, oh, I want to try this material now or change this thing out real quick. When you pick that one material, it's generally best to just run that one material. There are companies that run multiple materials if they have, compelling reasons to want to do that. If they're doing lots of builds on different materials, or they have a reason they change every couple months to a different material. But yeah, in general, this technology is, you're kind of locked in on the resin that you're going to be, you pick to start with. With that, we can go in and look at the rest of the NEO stereolithography workflow. And we'll just do a quick overview on this. But basically what happens is, starts out like a regular, any of the other machines. You have your STL file, your CAD file, you send it to Materialize Magic software. It builds the supports, it slices it, and preps it for you. Then send it over to the printer, we build it. Once it's done building, it raises up out of the platform. We're going to take it off the tray, wash them, because the parts come up, they're covered in a thin layer of excess resin. And then we're going to post-cure them, get them from their green state to their fully cured state, and then we're good to go.
So while you keep this slide up, Tim, I just want to point out one thing about the Materialize Magics component. If anyone on the call is not familiar with Materialize Magics, it's a third-party software for 3D printing build prep. It is absolutely industry standard. So the likelihood that you've already got folks on staff that are experts in the software is very high. It's also really intuitive software and really powerful. So it's a great building block of getting from your part file to the machine in not too many steps. And like Tim said, it handles part orientation, layout, support generation, and slicing.
Yeah, and we can actually see some little videos of how this whole technology works too. So once you've used Magics to slice and generate supports, and the supports for this technology is actually pretty interesting as we get the video going. It's very fine supports. So basically it's all breakaway support, right? We only have this one vat of material. So anything that has, big overhangs or heavy overhangs and we need to build support material to hold it up, it's a very light, delicate support structure because it's kind of like ice cubes floating in water or something. It's made out of the same material. So there's no huge density differences. So we don't have to worry about things floating or sinking. Only thing we're really doing is resisting, as we see in the video right here, that recoater as it goes across to cover the new layer. So it printed a layer. We can't even really see it because it blends in. Again, ice cubes and water, it's hard to see them. All we're doing is really resisting floating, drifting motions and stuff. So once it's done being printed, breaking away the breakaway support that is generated is actually very easy. It looks complicated. Luckily, the computer builds it all, and then it breaks off really easily with just tiny little nubs behind. So you can see it's building multiple parts on this build tray. The laser beam's jumping around, doing all different sections. It does the profile, and it does the hatchet infill, and it does it very quickly. And that recoater is going to spread back across this way. And then wash, rinse, repeat, or dip, recoat, rescan.
I would buy the machine simply just to watch this over and over and over again.
Yeah, when it's finished building and it's raising the whole finished build job up out of the resin, because again, it builds down into the vat. When it's done, it raises it up, and it just kind of makes sense why we need to wash the parts once they're done, we take them off, they just freshly raised up out of this vat of resin, and more parts just keep appearing. The parts are covered in this thin layer of resin that we just need to wash off. And you can do all kinds of different geometries. You see in the back middle there, we have a hollow bottle printed upside down. So once it's raised up, now you see it glugging. The resin that was trapped inside is just getting poured out now.
Back into the vat. Don't have to waste it.
To be reused. You see all this white stuff around the parts. We have these like clear glossy like glass parts, and there's this like white. All that white stuff is basically the support material.
Oh, we got the trolley.
Yeah, here's a trolley. So this can be useful. They have it for both machines. If you have a 450, you can get away, depending how big the build job you're doing, without using it. But if you have the 800, it can be very useful. Now, do you use the trolley much, Simon?
There's not a scenario in which I couldn't use the trolley. I'm a little guy to begin with, but these trays are very big. And when they're wet with resin and have heavy parts on them, there's no way that I could reasonably hold that tray up without covering myself in resin and injuring my back.
And so this tray probably also helps catch the resin stuff, because there might be more resin dripping down off this. We don't want to get around the office.
Oh, heck yeah. Keeps the floor clean.
All right, so then you put it on your trolley and wheel it over to this set. You want to explain what's going on here?
Yeah, sure. So what we've got is that whole tray. We haven't removed any of the parts from the tray, but it's here being submerged in a detergent. This is TPM, but there are a number of different detergents or solvents that you can use to cut away at that residual resin. Here in my facility in the Detroit, Michigan office, we use a product called a Demi from Post Process Technology. Basically, it's a detergent that cuts through the resin, and it incorporates agitation and ultrasonics to help do that a little bit more efficiently. What you're seeing here is more of a homegrown built-in tank system that has the TPM in it and some air lines underneath. And when the air bubbles out, that's causing the agitation. And once you've got the parts cleaned with the TPM, they're still going to need a little bit of post-processing time in isopropyl alcohol to clean off any residual detergent. So that's what you're seeing this operator doing right now. First, a dirty bath of isopropyl, and then a clean bath. But you can see that it really doesn't take a whole lot of hands-on effort or time in order to post-process these parts.
Another thing to note is that, I mean, most people miss this, I'm sure. When they were taking the parts off and putting in that first bath, took them off the tray, removed all the supports, and then put them in the first bath. And that's how easy that breakaway support comes off. Like, they just took it off, they ripped them off, threw it straight in the trash, and then put the part in the rinse tank. And they did it so fast we didn't really notice it was happening.
And in that the very end of that last video, that operator on the left-hand side was just blowing compressed air on the parts to make sure that no residual liquid IPA was on the surface.
That just helps dry them off quicker too, right?
Oh yeah.
So then the last step is that we actually need to do a UV post-cure on the parts. So the parts come out, they're at green strength. They're most of the way cured. They're probably 80% of their total strength. But to get a full final cure, 100% like spec sheet strength, we need to do a UV post-cure. So we have these big UV ovens. It's just light bulbs kicking out specific UV wavelength, and rotating trays, glass wall or mirrored walls to bouncing around. But we just do this for a couple minutes depending on material, and it's like what, 10 minutes per side or something.
It's material dependent, but yeah, it's not going to exceed very much beyond that, and it's completely hands-off time. There's not an operator that needs to stand there flipping parts. This called post-curing apparatus does all that hard work for us.
Right, and then you have your final parts. Yeah, it's not a lot. It's more hands-on time for this stuff than say FDM or something, but not a lot. It's just that initial getting the resin off the surface, and then you're about the same as all the other technologies now.
Yep.
All right, so let's take a look at some different material options we have. And we'll just talk about some options here. We don't want to spend all day talking about these and boring you guys at all, but you kind of see when you fill up a whole vat of material, it ends up kind of looking pretty cool depending on what you got loaded. But there's two levels of materials here. So we got the Somos materials, which are all pre-approved, kind of dialed in stats and recipes for them. So we have things like watersheds, which they have watershed clear, watershed black, almost tarous material. These all have different advantages that, depending on what you want to do with them. You know, the watershed clear is very nice clear materials. It's very strong, ABS-like strength. Taros is a black opaque material that, you know, really shows details well on surfaces. If you want to get into like high temperature, we got a Perform resin, which actually has ceramic powder suspended in it to get that really high temperature, stiff, durable parts. And then, you know, depending what you want to do, we got master casts patterns we can do, investment casting, one tunnel models. We got resins that are good specifically for those different areas. You can see some go across multiple categories.
And I was going to say one of my favorite materials that isn't listed here yet because it's a little bit of an older slide. There's a version of Watershed called Watershed AF, and whatever you think the AF stands for, it doesn't stand for that. It stands for antimony free. So Watershed AF is used explicitly for investment casting patterns because the material Watershed AF, by removing the antimony when that material burns out of the investment cast, it leaves little to no ash, where before Watershed AF had been developed, just using a standard SLA resin or an SL resin, you could use it for investment casting patterns, but didn't always burn out as cleanly as a foundry would want it to. So this Watershed AF is optimized for that kind of an application.
Yeah, and it's just it's an upgrade on their initial Watershed XC recipe. They also came out with a Watershed or a Water Clear Ultra. So it depends, you know, what you're looking for out of them. But yeah, and these are all like the pre-approved, like we've already got everything dialed in. You can, you know, hit the ground running. From there, you can go to open materials. If it cures at 355 nanometers, then you can run it in the machine. All you have to do is go and dial it in, and then most resin, you know, companies that are making these resins, they're going to have a spec sheet for you about like, oh, hey, here's our recommended settings. And then, so you have an easy spot to dial in from. You're not very far off the target from those. So it's not like a super in-depth process. It's not going to take a month to get figured out how to run it. It works pretty well. Have you heard any materials you like to try and run on the open ones, or?
So it's interesting that you asked that question, because I was just about to say one of the more interesting applications that I have heard about in the last couple of months, or prospective customers in the last couple of months, was a legacy user. I'm not going to name the name of the printer manufacturer, but the folks who invented stereolithography way back when. They're still in the business. They've been developing materials for a very long time. It's a closed ecosystem, though. This customer was ready to upgrade their hardware and chose to go, or they are choosing to go with a Neo stereolithography printer, but they're very happy with the results of the prints that they get from a material standpoint from their legacy machine. Well, those legacy materials also cure at 355 nanometers. There is nothing that is going to prevent them, and they're going to purchase this machine based on the fact that they're going to be able to use another manufacturer's resin, a competitor's resin, but on the new, improved, optimized Neo platform hardware.
All right, yeah, it's lots of advantages to having this new Neo platform to work with. We do have some information about use cases or case studies, and we won't spend too much time diving into these, but we'll run through some options real quick just to give you guys some ideas about what other people are doing or how people are using these, and also kind of give you an idea of the quality and the parts we can get off the machines. And you know, for the Neo 450, people tend to use this for doing quick iterations or really small, fine detail parts. I mean, you can see the details that we can get on these Neo machines are very impressive. I printed flat parts on here that have like a mirror finish, like scraped off the machine, clean them up, bust off supports. The side that didn't have the supports on it has almost a glossy, reflective finish on it, like an injection mold. It's impressive. So again, I mean, we can see all the writing on there for, you know, Cheney Coopers. And again, this is a single material machine, right? We're not using black resin to make that text. It's just the details and fine tuning on it is very crisp. And then for the Neo 800, again, single material prototyping, of course, but good for high volume printing or very large part printing. And again, you can see the support grids, it's built on that. So in that large part, all that white stuff around it, the blue-ish stuff is the actual part, and that white stuff is the support material. And that all just breaks away by hand. It's actually very light, open, thin build structure. So it doesn't waste that much resin compared to what your big solid part or whatever is going to be on there. And with these machines, as we were kind of mentioning in the beginning, you know, they're not for everybody, right? It's not a one size fits all. It's a, you know, single material you're going to kind of stuck with unless you get a whole nother bat. And you know, to help justify something like the Neo 800, you have to have, you know, be doing multiple print jobs a week on it, or be printing really large parts that are really expensive to go out of house to get made, to get one of these in. It's not just it fits every application kind of situation. But there are some really cool materials out there. We have you know, a case study here from TDF1 where they've used a bunch of different materials for doing, you know, parts on their race cars. And one of the resins they really liked was Perform, because it's very stiff, you know, high temperature resistance, you know, low shrinkage. And they're using it in their wind tunnels. They can use it for rapid tooling, for actually making carbon fiber pieces or whatever off of it, for putting in their race cars for, you know, composite motorsports.
Well, and Tim has mentioned wind tunnel models for a couple of these slides already, and it's important to point out this application because a lot of folks use stereolithography specifically for wind tunnel testing. And that's because the parts come off of the machine already injection molded quality. So there's very little post-processing that needs to be done to get a part that is no longer going to suffer from any kind of artifacts from 3D printing. Like you couldn't do an FDM part directly off the printer in a wind tunnel because the air is going to move over those ridges, the layer ridges, differently than it would a fully finished part on a vehicle. What's great about stereolithography, especially doing wind tunnel testing out of parts made in Perform, is they're coming out of the machine ready for testing.
And yeah, and then the stiffness is also a big one on there too, because if you're putting in a wind tunnel and you do have little pieces on it, and people, you know, you do print little buildings or whatever and do their wind tunnel test of like a city plan, you don't want your little smaller pieces actually deflecting and deforming on you while you're, you know, putting high pressure winds on it. So you want things to be stiff, you want them to be smooth, you want the wind to actually flow around them. And like, I mean, so these parts over here, again, pretty much all the parts we show, but there's no post-processing and sanding or tumbling. Like they're off the machine and they're just glossy and smooth and very nice quality off of these. But one of the options they've done, the other thing you can do instead of wind tunnel, was you know, molds. So composite mold assembly. The 5-piece mold, they're able to print it, you know, a day and 17 hours of high quality printing time to get all these parts. And these are big, solid molds. You're not really too many restrictions for geometries in here, right? So it's not like, oh, there's a big fat cross-it, the part's too thick and solid. You don't have to lattice them out. You can print them on here. Now, and because they had big lead times to do traditional manufacturing to get these, so now they can do faster iterations. You kind of see how they were able to fit all of it in one build job, orient them in there so they're up in the Z-axis, helps minimize your cross section. And then all the red stuff in that picture, again, that's the support material that generated around it, and there just breaks away by hand, breaks off real easy.
And we talked about material limitations in this machine being limited basically to one material, but this is an application where even though the material has the material is a photopolymer that has limited mechanical properties that can't really change, this is using that material as a layup tool. So we're effectively making parts with this machine out of laid up carbon fiber. Even though we're not printing in that, we're able to get a finished F1 carbon fiber racing wheel with very little post-processing work in making those layup tools.
That's right. Another layup tool. So this is one, and here's another one. There's also composite layup tools that they're printing. So instead of having to machine all of these parts and the long lead times, They literally printed them all, a massive tray of them like that. Break them off, they had a nice smooth surface finish already, and then that's the carbon fiber part they were able to get out of it on the bottom right there, that black one. And you can see even it has the logos and everything, and it was all built into the mold. And then you just carbon fiber layup on it, and you're good to go. And it's a great way to get to use end use parts in additive manufacturing without having to specifically have the end use part be the printed part. And we've seen that in lots of different applications.
I'd also like to say this tray with all these perform tools on it, when you asked the question about whether I use the trolley or not, this would be a very heavy platform. There's not a planet on which I'd be able to lift that on my own.
Yeah, especially because, I mean, that's 800, right? So
yeah,
that's almost 3 feet by 3 feet around there. So, and that's ceramic material, so it's pretty dense, heavy material. It's
oh yeah.
Trolley makes life easy for everybody, though.
Oh yeah.
Another material that you'll probably hear about a lot is the watershed resin. Now, this is one that's been around for a while. People love it. They've come up with those new recipes for it, the watershed AF, the water ultra clear. And again, good clarity, strong functional parts, low water absorption, good resistance to lots of different chemicals. So people print all kinds of different fluid mechanics setups for it, so they can actually watch the fluids go through it and see how it reacts. Or use it to actually, see inside of other things. So if you're building a big assembly or something and you want to be able to see how things are assembling up inside of it, check for clearances and room, having a see-through part makes life real easy. This specific part, I mean, just fit on a Neo 800. It was so large, and they were able to cut their lead time down from 2 to 3 weeks to CNC this giant part with a ton of waste you're having to cut out on it to 3 days, right? And then also half the price. And the size of this part, I mean, you can see here's the visualized full build chamber of an 800. So we're going 800 by 800 by 600 deep, and it's using almost all of it. The last picture show, yeah. So yeah, all that lattice work you can see back in there, it looks like, delicate lace. That's the support material. That's all generated automatically, and all just you grab it, with your gloved hand, and it just peels off with the delicate support attachments, because we're not trying to adhere to it strongly. We're not resisting any strong forces. So everything can be nice and delicate and keep the focus on the part and the surface quality and finish.
Well, and another point about this watershed material that Tim is highlighting right now, I don't want to say the majority, but if a customer were to say to me, Simon, I want to get a Neo, I want the most general purpose material possible, maybe something mimicking ABS. I don't know exactly what my applications are supposed to be, but I know I want the technology. Watershed is going to be my answer to that request. There are, right, as Tim was pointing out, there are a bunch of different materials for different mechanical requirements, but watershed is like the easy go-to for a combination of strength, clarity, chemical resistivity, and economy, because it's one of the cheaper materials as well.
Well said. And with that, and again, we had all those other materials. We're not going to do a slide for every individual one, but people use all kinds of different materials, all kinds of open materials, and high reliability on these machines. If you guys have any questions, you can throw more of them into the chat. We answered a couple of them that came through. You can email us directly. You can go to our website, goengineer.com, to get some more information. We'll have some more webinars about the stereolithography machines coming up in the future, going more deep dive into the machines themselves and the differences between them and whatnot. So,
Tim, I for one have appreciated all of the puns involving diving and getting wet, just because that is so apropos to stereolithography.
It is, and it's one of the things that really separates it from those other printers, right? Is that you got this big vat of liquid resin. It makes it a little bit more intimidating to get into, but as we were talking about, it's easy to use and easy to handle, and nothing too scary about it. So why not make puns about it?
Well, and I appreciated you using the language easy to get into, because the Neo 800 vat, like, you could fit quite a few of me in that vat. You'd need scuba gear ultimately, but it's not small.
Mannequin curled up in there.
Oh, we're such serious application engineers.
All right, well, with that, thanks for attending our webinar. And if you have more questions, feel free to reach out. Until then, we'll see you guys next time.
Thanks, everybody.